Hey everybody, and welcome back to Calc 3 Online. So the plan for today is just do a few more examples related to these limits from multivariable functions. This one is, it's got this picture over here, and you can kind of see it. I'm realizing now it's a little harder to tell, but as you approach the origin, you can see that like the origin's like basically right here, and there's kind of these like two different like heights here. And I just got this again from that Math 3D program, so you can always go and like plug this in to see it a little better. But sometimes you just need to be kind of clever with how you choose your path in order to try to show that something doesn't they actually don't get the same value. And so you can see in this one, if you basically approach on y equals x first, okay, which would look like this. So you'd have, instead of like xy, you'd be kind of doing like xx. So the limit as like x and y equals x approaches 0, 0 of the function, it will turn into x squared on top, right? X times x. And then the y squared on the bottom becomes an x squared. And so this... I can simplify a little bit, and then you can cancel that, right, and you can get a half. And if you do some, kind of looking at the picture or just kind of looking at the function over here, you can see that if you made like the line, if you took it on the path y equals negative x instead, then you're going to get a negative here. You're not going to get a negative down here, but that's actually good because then you're not going to get a double negative, and you're going to get a negative a half instead of a positive half. So what I mean by that is if you approach on y equals negative x, this other path, then you would have x times negative x up top is negative x squared, right? And then if you square negative x for the y part down there, you're still going to get x squared. So then you would get negative x squared over 2x squared, and then that cancels and gives you negative a half. So, now like you can just say something like, since 1/2 doesn't equal negative a half, the limit does not exist. And these things can be kind of hard to come up with. The way that I kind of see it is just that I realize I can introduce, the bottom will stay the same with introducing a negative, but the top will not. So that's kind of like a giveaway that I should be able to get something different. You can also just kind of look at the picture here and see that you get kind of two different things around the origin, depending on if you're coming in from the y equals x or y equals negative x diagonal. So this is actually one from the homework, and I think it's just a good one to go over together. It uses just an algebra trick that you do with limits and in like Calc 1, but maybe you haven't seen it in a while. And that trick is the thing called the conjugate. So anytime you see something like this, there's like the complex conjugate for imaginary things too, but anytime you have roots like this, if you multiply by what they call the conjugate on top and bottom, so the conjugate in this case would just be the plus version of that. So if you do this on top and bottom, right, this whole thing is just like a weird, funky 1, so you're not changing anything. But a lot of times when you see this in an algebra problem, if you multiply by the conjugate, which is just the same thing with a plus there, on top and bottom, something nice is going to happen. So in this case, if you go and just multiply out this part right here, then you're going to get... Well, actually, I'm going to take out an x2 from the top there. So I'm going to factor out an x. Oops. So that's just the top, right? And then the nice thing on the bottom, when you double distribute this and this out, you're going to kill that square root, so you're going to get an x. And then you're going to get a plus square root xy and a minus square root xy. So they'll cancel. And then you'll just have the minus square root y and the plus 1. So that's going to cancel to a minus x minus y. And then this is nice because this and this can cancel, right? And now you have just this part left over. And that is a nice thing you can take a limit of, right? So now you can just do direct substitution. So another like common trick here is just if you see something like the conjugate, just multiply top and bottom by 1 like that. You can totally do that. And then you get it into like this form now. And this thing is much nicer because you can just do direct substitution. And if you do that right, you get 0. The picture isn't so good. Actually, what's kind of happening is it just didn't graph well for some reason. But basically, this should all be blue too. But it's kind of like a weird, it like curves up here. And it kind of like lowers itself as it goes. And then it's steeper out here. But as you approach the origin along any path, and if you come in, you're always just getting 0 in the z. So that's how this one works out. So I said something about this kind of briefly last time, but I thought I would add a little more here. So the reason L'Hopital's is hard is because there's just so many different paths to approach on. And there is technically a way to do it. You need something called a directional derivative, which is something that we talk about later on, actually in this chapter, but not quite yet. And I actually posted something in the Google Classroom under the resources that if anyone's curious and wants to read, but it's kind of complicated. But you're not going to be asked to do anything like this article does, but it technically is a thing, and not even a lot of people use L'Hopital's. The one thing I was going to add is, so sometimes, like, take this thing. If you were asked in the real world to, like, find this limit, you might be able to figure it out somehow using some sort of algebra trick or something, but honestly, most people, they just go to programs that do like 3D graphing, like 3D GeoGebra or the Math 3D program, things like that, and they honestly usually just plug it in. Also things like Mathematica does this, and things like Python that can do it, but you can just go and look at like plots of it, and you can just kind of analyze what's happening near the origin. So it's usually more like in the real world, people just look at pictures of it like this. There are times where this gets done, and it's important to know these tricks out there, but it can be really hard to like show that a limit exists. You have to use usually tricks like the squeeze theorem or something like that to really prove that one exists. Or you need these algebra tricks. And sometimes that's just too hard. And so then you're just left with like taking some big messy thing and just going and plugging in something to like a 3D graphing program. So I actually want to do one more example. So I've sort of, just to kind of sum up so far, so we've got squeeze theorem we saw last time to show that something exists. We've got, modeling programs like this or this to kind of try to analyze whether or not it exists. But the most common thing is usually the algebra tricks like this to show that they exist. To show that they don't exist, it's really always just one thing. It's always just go along some set of 2 different paths and show that you get 2 different numbers. Now, sometimes it's a lot harder to come up with them, like y equals x and y equals negative x. aren't too bad here because you can kind of see it. You can get like a plus minus difference up there. But I want to do actually one more. And I realized I didn't include it here, but that's fine. We can just do it on a white thing for a change. So the problem I want to do is this one. And the reason this one's a little trickier is because you have to pick kind of a weird path. So it doesn't matter what path you come in on, as long as they are two different paths and you get two different values, then you've shown that the limit doesn't exist. So I can prove that this limit doesn't exist. And the first one that I'm going to do is just along the line y equals x. Okay. And in this case, I'm going to instead be doing basic limit of x, going to 0, 0. And then all my y's just become x's, right? So I get x to the 4th up here, and then x to the 6th plus another x squared. And in this case, then I can factor an x squared out. And I would end up with x squared over x to the 4th plus 1, right? And now, if I do just direct substitution, I would get basically a 0 over 1, right? And so that's going to be 0. And then the reason this one's a little tricky is, like, if you try, like, y equals negative x, let's just even kind of show you briefly what happens. So you would have negative x to the 4th up top, and then you'd have x to the 6th plus the negative x being squared would give you x squared, right? And then if you do the same kind of stuff, you take out an x squared, you're going to have negative x squared over x to the 4th plus 1. But the problem with this is when you do direct substitution, you're still getting 0. So you're not getting, two different things. And it also does not mean that the limit equals 0. You need to get, you basically just need to keep trying until you either come up with an algebra system where you are 100% sure, like we did in this one, that you can just do direct substitution for like some sort of continuous function like that and then get the answer, or you need to come up with a clever other path. And the way that you can do this, these two being different on the bottom, you can plug in something for y so that these are not, it's not a binomial anymore, so that it's actually going to be a monomial, and you can just combine these things. So let me actually erase some of this because I don't want that. So you basically need to square something and get it to be x to the 6th right here, right? And so that means that the y value should be x cubed. And if you come in on this path, okay, so you're going to have limit x cubed this time. And you can do this. It can just be any path in, along literally any curve at all. The curves are not, it does not matter really which ones you pick. So x to the 6th is now up top, right? And then you're going to have like x to the 6th plus x cubed squared, which is another x to the 6th. So then you're going to get, I'm going to just write all this down. You're going to get x to the 6th over 2x to the 6th. And then those can cancel, and you're going to get 1/2, right? And this is kind of another like just common like trick to show that the limit doesn't exist, is if you can kind of structurally change the expression between the two cases. So here I had a binomial on the bottom, and here I made it so it's going to be a monomial. And there's really no like magic formula in terms of how I do this. You just sort of have to be sort of clever about it and look at these things and think about how the algebra is going to work out to give you like two different things. So then it's always good to just kind of sum this up, since the limit as you approach along the path y equals x, I'm just going to call it like this function. Oh wait, it's not a function of one variable then. So this function, since that limit doesn't equal the limit along another path, right, then we conclude that the limit does not exist. All right. And that's it. I think that's a good one to show too, just because it kind of uses like some kind of clever path to show it doesn't exist.